This conference will now be recorded.
Yeah, so we'll start the session. So good morning to everyone. So let students join. So before that we'll have a screen sharing. So we'll start the session with a video. So where the video was made by NITAR Bombay. Okay, so NITAR is something like National Institute for Technical Training and Research. Okay, so there they do a lot of technical training for the faculty, students, and all. So they prepared a small video on prestressed concrete. So it's a bit bigger one. Okay, so please try to go through that video once. So wherever we have any doubts in that, so by that we can get clarified with the video. Okay, so let me share you that video. So by that we all can view that.
It's a very vital man-made construction material used for constructing structures like buildings, bridges, water tanks, etc. It is an intimate mixture of cement, sand, coarse aggregates, and water, suitable design to proportion. This plain concrete is very strong in compression, but very weak in tension. Tension induces cracks, leading to the structural or functional failure of concrete. So wherever tension comes, steel reinforcements are placed and embedded in concrete. By the bond action, this steel is firmly held by concrete so that tensile stresses are transferred to steel reinforcement and the compressive stresses are transferred to the concrete after the application of the load. This reinforced concrete is uneconomical and functionally ineffective when the span or height of the structural members is very high. When the applied load has more intensity and becomes dynamic, as in bridges and in places where no cracks are to be developed, like water tanks for functional requirements. In such situations, reinforced concrete is replaced by prestressed concrete. Let us now consider the example of a cycle spoke. The diameter of the spoke is very small compared to its length. When the axial compressive force is applied on that, it easily buckles. But when it is subjected to heavy loads as part of the cycle wheel, it doesn't buckle. This is because it is pre-tension. The already induced pre-tension neutralizes this compressive stress after loading, so that the net stress is either zero or tension. As no compression is ultimately developed, buckling is prevented and wheel shape is maintained. This same concept is extended to concrete also. The pre-compression is induced in concrete. When the sections are subjected to tensile stresses due to loading, they are neutralized by the already induced pre-compressive stresses in concrete, so that ultimately the net stress is either zero or compression. Tensile stresses do not occur in concrete at any stage. Hence, pre-stressed concrete is a crack-free material, and so it is homogeneous, whereas reinforced concrete is a cracked material, and so it is heterogeneous. In any pre-stressed work, the steel used is tension, which in turn induces the necessary pre-compression to the concrete before the external load is applied. Whereas in RCC, the steel and concrete take the tensile and compressive stresses respectively due to loading. This pre-stressing is classified into many categories. The two main categories are linear pre-stressing and circular pre-stressing. In linear pre-stressing, the steel in straight or parabolic profile is tension, which transmits pre-compression to concrete. This is done in linear members like girders, columns, slabs, sleepers, electric poles, etc. circular pre-stressing, the process is applied to circular structures like water tanks, silos, and pipes. Here, high tensile steel wires are wound under tension in circles around the structure. The tangential force in the wires creates an equal and opposite compressive stress in the concrete. This compressive stress in concrete is uniformly distributed over the cross-section. Depending upon the extent of pre-stressing, the process is again classified into full and partial pre-stressing. Full pre-stressing confirms to low tension under working load, which is one end of the spectrum. RCC is at the other end of the spectrum, which is a cracked material. Partial pre-stressing finds a place in between these two. Here, the tensile stresses are partially neutralized by pre-stressing. For the unbalanced tensile stresses, steel reinforcements have to be used. These steel reinforcements are given anti-corrosive treatment coating prior to their placement in position. This partial pre-stressing prevents an undesirable camber or full pre-stressing in the initial stage. Another classification of pre-stressed concrete based on the tensioning operation is pre-tensioning and post-tensioning. In pre-tensioning, the steel is tensioned before the concrete is placed. The anchorage and jacking abutments may be as much as 800 feet apart. The steel is tensioned over the full length of the casting bed at one time. It is temporarily anchored against some abutments or stressing beds when tensioned. A number of individual members are cast along the stressed steel. As the fresh concrete hardens, it bonds to the steel, and the concrete has reached the required strength. The jacking force is released. The steel tends to shorten, but is prevented to do so due to the bond with the concrete. Hence, concrete is pre-compressed. Then the steel is cut free between the members. Great saving of labor is affected due to this condition. This long line method is used in precasting.
Guys, this is what we spoke about yesterday, Hoyer method, right? So Hoyer method is nothing but long line method where you can cast multiple elements at a time, okay, with a single unit, okay. So in that way, so this long line method which right now was there in the video, so you can try to relate that pictures, everything with this particular video, okay.
Plants or laboratories where permanent beds are provided for such tensioning. It is also used in the field where abutments can be economically constructed. Here, only straight profile for steel can be used for pre-tensioning. Hyperboloid roofing shells, sleepers, etc. can be produced by this method. Post-tensioning is a method of pre-stressing where the tensioning of steel is done after the concrete has hardened. This process can be applied to members either precast or cast in sight. Post-tensioning is normally used for massive constructions using big girders. For example, in the case of laying elevated railway tracks, post-tension box girders support the tracks and span between the trussel beams. The trussel beams are supported between massive columns, which in turn are supported by pile foundations. The frames, with trussel beams and columns, are bearing the box girders. In such cases, box girders are preferable than bi-section girders, as their moments of inertia about their rectangular axis are more, and hence the stresses are reduced. Also, their torsional rigidity is very high. Interiors of box girder bridges can be used to accommodate services such as gas pipes, water mains, etc. In larger spans, bottom flange could be used as another deck to accommodate traffic. The maintenance of box girder is easier as interior space is directly accessible. So box girders are popular practical sections for bridges and elevated transporting systems. In the case of massive constructions like a play stadium, the roof can be made from precast, post-tensioned hyperbolic paraboloid shell elements, which are ideal from a structural and architectural point of view. In the box girders used for elevated transporting system as in railways, the top and bottom slab portions are designed as reinforced concrete slabs. Main reinforcements run parallel to the width, and secondary ones run parallel to the length. A cantilever span is also provided on one side to accommodate the footpath. The webs are pre-stressed. Vertical shear reinforcements are provided in the webs to take shear force as an RCC. Normally, the pre-stressing steel is used in the form of strands, where each strand consists of several tendons or plies. Strands are made by laying a number of layers of plies in helices over a central core. A single straight wire forms the core. The remaining wires are laid in helices. The properties of strands as a whole is to be considered in the design. For example, in BBRV system of pre-stressing normally, 7 plies or wires are there in one strand. Here, each ply is about 4 mm in diameter. 12 such strands are there in one cable. These strands are obtained in coils. The required length is measured and cutting is done. The set of strands are inserted into galvanized iron tubes known as sheathing or cables. Couplers are used for joining the various pieces of sheathing. Then these cables are kept in position in the webs of the box girder in a parabolic profile. Various cables are kept at various ordinates. Normally the bottommost one is straight, and the top ones gradually curve upwards at the ends, based on design.
See, now you can see the profiling which was done in a parabolic shape, isn't it? Right? See why this profiling was in a parabolic shape? Can anyone? Why can't it be straight? Why the profiling was in a parabolic shape? Why this profiling was in parabolic shape? Ila enduku parabolic shape lo undamma? Why can't it be straight? See, when it is in a parabolic shape, when you try to stretch the strands, okay, when you try to pull the strands, okay, after concreting and after concrete sets, after attaining its characteristic compression strength, then we do post tensioning, right? When you try to pull the strands will try to become straight, isn't it? So by that it will try to push your concrete towards upward direction. Okay, understood? So the steel wires will try to become straight. Okay, in that moment it will give the upward forces to the concrete, where the concrete will become off. So that is what happening in the post tensioning system, right? So that is the reason why at a proper design way they are going to be profiled in parabolic shape. Okay, so that even the staging of post tensioning is also going to be done in different stages. You can't do all strands at a time. Okay, the stressing, or I mean the stressing what you are doing, you can't do all strands at a time. So there is a different stages. You need to follow that stages to do that post tensioning, where the concrete will be subjected to post compression into it. Okay, so that is what you need to understand. Okay, so that profiling, the design of profiling, also everything we are going to study in the third unit. Okay, continue.
Box girder in a parabolic profile. Various cables are kept at various ordinates. Normally, the bottommost one is straight, and the top ones gradually curve upwards at the ends, based on design. These cables are anchored at the ends. The strands pass through the conical end of the bearing plates. These plates have a grouting hole also. Then the strands pass through the holes of a circular plate outside. wedges are driven to keep the tension strands in position to retain the applied stress. This is the arrangement at the end of the ladder. This BBRV system is different from the CCL system in the stressing operation. In the CCL system, the cable consists of strands again, with each strand made of plies wound in a helical form. But instead of pulling all the strands in the same cable at the same time as in the BBRV system, here strands are pulled one after the other. The jacking and pump arrangement are designed accordingly. As mechanical anchorage like wedges are used in such systems for locking, they are called mechanical pre-stressing systems.
See, in this mechanical pre-stressing system, here what he is talking about a BBR and CCL system, right? So in BBR system, each strand is supposed to be pulled, okay? But in CCL system, whole bunch of that strands can be stressed with the help of huge jack, okay? So that's why this single jack is called as a uni-stressing jack and matter, okay? So if you try to use a big jack where it's gonna hold all the strands at a time, so that is called a multiple jack, okay? So it's called multiple jack. This is called uni jack. Uni jack and a single strands ni pull చేస్తుంది అన్నమాట, okay? Multiple jack, it will pull all the strands at a time, okay? So if you see in the bridges, okay, in bridges they are going to use multi jack, which it gonna pull all strands at a time, okay? So this single jack is gonna used for slabs particularly. Why? Because there will be a single strands takes place, so it can be pulled by each strand individually, okay? In that way you need to understand where it can be used, like single strand jack and multiple strand jack, okay?
And anchoring is done by mechanical means. Hydraulic jacks are normally used in mechanical systems, where the tensioning operation is done by a hydraulic or oil pump. The pressure is monitored by the dial gauge. As the tensile force is applied, the ram of the jack moves out. The outside projection of the ram indicating the extension of the strand is measured. Operation continues till the required extension is obtained. The conical wedges are driven to retain the stressing strands in position. The stressing of cables is done in various stages. Extra or substitute cables are provided in the member. When a failure occurs in any of the tension cables, these cables are used as a substitute. Different mechanical systems are used in different countries. They are Hoyer, BBRV, CCL, Freyssinet, Magnel Blaton, Morandi, Gifford Udall, McCall, etc. All these systems have two basic operations only. They are stressing the steel and anchoring it to concrete. The method of applying the pre-stress, the size and number of wires or strands used, and the mode of anchoring differ from system to system. Along with these normal mechanical pre-stressing systems, chemical and electro-thermal systems are also popular nowadays. In chemical pre-stressing, expanding cement is used. The ingredients of this cement are normal Portland cement, blast furnace slag, and ground clinker consisting of diacalcium silicates, aluminates, and calcium sulfates. Pre-stress is applied in several ways. Concrete member of expanding cement expands during hardening. When the ends of the member are firmly held, the expansion is prevented when the concrete is pre-compressed. In the second method, member is constructed with normal cement. The gaps between the ends of the member and the rigid supports are filled by the expanding cement at both ends. This cement on expansion applies the compressive stresses to the member. In the third method, the concrete member is made by the expanding cement, in which the steel is embedded. When steel resists this expansion, compressive stresses are produced in concrete. Two-way slabs, pressure pipes, and hyperbolic paraboloid shells, etc., are pre-stressed by this process. This modern method of pre-stressing has not become very popular due to many practical difficulties. In the electrothermal pre-stressing, tendons are stretched by heating them by an electric current. This is done on a heating stand of 10 meters to 24 meters in length. The stand may accommodate 3 to 4 bars at a time. The heating stand consists of two end supports with brass contacts for clamping the two ends of the bars and a few intermediate supports. One of the clamping contacts holds the bar rigidly, while the other slides freely on rollers mounted on one of the end supports to prevent the elongation of the bar. The rods being heated are arranged side by side horizontally. The heating is done for a very short period to raise the temperature to 250 to 400 degrees Celsius. Such heating for a few minutes does not anneal the steel. The bars are lifted from the stand when they are hot and placed in the slots of end plates of a mold or a pre-stressing bed and locked. When the bars cool, they pre-compress concrete. This method has several advantages. High yield strength informed bars of Fe 500, Fe 800 may be used instead of high strength pre-stressing steel. Expensive grips and anchoring devices are avoided. Use of deformed bars reduces the transmission length, which is critical in short retention members like railway sleepers. Unlike mechanical pre-stressing methods, no maintenance problems are posed. Less labor force is required. Generally, the capital investment on the plant is very much less. Flooring and roofing elements, precast trusses and poles are manufactured using this method. Whatever be the pre-stressing system used, 3 stages are to be passed through by these pre-stressed elements. They are initial stage of tensioning, transfer stage where concrete is pre-compressed, final stage of load application. As there is a time lag between the transfer stage and the final stage, the available pre-stress is reduced in magnitude. This loss in pre-stress is an important criterion in pre-stressed concrete. These losses are due to slip and anchorage, elastic shortening, relaxation of steel, creep in concrete, shrinkage of concrete, and friction and wobbling effect. These losses are taken into account precisely in the design because overestimation of the losses leads to undesirable camber, and the underestimation of losses leads to cracking. As these losses are taken into account, the cables are stressed high. So high-strength steel is used for pre-stressing purposes in mechanical systems. To economize the process, commercial anchorages for pre-stressing steel are designed on the basis of high-strength concrete. Weaker concrete may fail under the application of pre-stress. Such failures may take place in bearing, or in bond between the steel and concrete, or in tension near the anchorages. In order to bear higher stresses in all stages, high-strength concrete is used for pre-stressing purposes, unlike reinforced concrete. Under normal circumstances, the loss in pre-tensioning units is around 18%, and in the post-tensioning units, it is around 15%. Hence, minimum of M40 grade is recommended for pre-tension work and M35 for post-tension work. In pre-tension construction, the pre-stress is normally transferred to the concrete by a bond over a length, which may be equal to the member depth. No problem arises due to the gradient stress input. On the contrary, for post-tension elements, the pre-stressing force is transferred through the bearing of the end anchorages and applied in full at the extreme end of the element. Hence, the end zone of the elements called end blocks have complex stress concentrations. Pre-stress in the concrete changes from concentrations at the anchorages to the calculated stress distribution so that it is subject to high stresses. The end block is subjected to high compressive and shear stresses with transverse tension. Adequate shear and spiral reinforcements are to be provided at the end block as per design. Even in the case of flanged beams, end blocks are made solid and usually rectangular to provide the necessary bearing area and to prevent excessive stress concentration. In box girder sections, the thickness of webs at the end block region is more and gradually reduces to the desired value for this purpose. This is a vital concept in post-tensioning systems.
See what it is talking about. In post-tension system, end blocks, so that means end supports, are supposed to be more stressed. Okay, so that is the reason why in post-tensioning elements like girders, box girders like this, the end diaphragm or the end dimension will be more in thickness compared to the thickness of the same element at center. Okay, so if you take an I section, the I section diameter is more at support and it will converge towards center. Okay, so that is the reason why you can see the convergence of higher diameter, higher thickness to lower thickness in girder, even in the box girder. Okay, so this is the convergence. So please follow my cursor. This is the converging part from more thickness to less thickness. Okay, so this is the less thickness of the girder, this is the more thickness. So this is the convergence takes place. You know how the tapering takes place, right? So this is the way how the convergence of girder going to take place to reduce its thickness towards center. Okay, so that you can able to see it clear.
Post-tensioning is preferred in many cases because the losses are less compared to pre-tensioning. Parabolic cables are possible in post-tensioning. The tensile pre-stress in the parabolic cable is tangential to the cable. Due to this condition, horizontal and vertical components are produced. The horizontal components get neutralized, and the vertical components neutralize the vertical downward forces to some extent. Hence, the shear effect is reduced. For the unbalanced shear reinforcements are provided. These upward forces due to pre-stress are more than the downward self-weight of the element in the initial stage. The deflection due to the applied downward force at the final stage interacts with this initial deflection. Hence, the final deflection is considerably reduced. Thus, the structural and functional requirements are catered to by the These upward forces due to pre-stress are more than the final deflection is considered.
Have you understood this concept, right? So this is very, very important. So this is what the pre-stressing technology came into existence. So just to reduce the deflection of the beam where it can avoid 100% cracks in the beam, right? See, this is the final deflection which is toward downward direction. Okay, initial deflection which is upward direction. So balancing together, so where you can see very less deflection in your pre-stressed element. Okay, so this is what you have to understand by compressing your concrete element towards upward direction, right? So which is going to be replacing, I mean, which is going to be reduce the deflection of your parent element. Okay.
Considerably reduced. Thus, the structural and functional requirements are catered to by these parabolic cable profiles. As stated earlier, the high-strength concrete is produced by a special batching plant. The ingredients are mixed thoroughly as per the designed proportions and loaded from the batch mixer to the transit mixer, which carries the concrete to the required place, keeping the mix agitated. The concrete is then pumped by pressure through pipes and pouring is done. The compaction is done by shutter vibrators and poker vibrators effectively. In massive constructions, steam curing is done. Steam is generated from the boiler and passed through curing pipes. After concreting is over, the post-tensioning is done using a suitable system. In order to provide permanent protection to the post-tension steel and to develop bond between the pre-stressing steel and the surrounding concrete, the cement grout, with or without admixtures, is pumped into the sheathing through grout holes using grout pumps. If it is an elevated construction, like railway bridges or laying elevated railway tracks, as in metropolitan city transport systems, heavy box girders are cast on the ground level, which are precast, pre-stressed units. Casting them on the ground in the yards can be done effectively by easy and convenient operations. The quality control is good. These precast, pre-stressed girders are lifted to the required height by the heavy jack arrangements. They are then carried on trolleys to the required position and lowered by means of jacks. Neoprene pads are provided below these girders to impart flexible movements at the supports. If it is a massive structural work like a stadium, it could be carried to the required position by cranes. Because of the use of high-strength concrete and steel, and as the elements are stressed even prior to loading, stringent quality control measures are to be observed. Hence, the quality control labs are established at the site itself, and the quality is tested and controlled continuously in order to ensure an effective, stronger, and economical construction using pre-stressed concrete.
Yep. So guys, now tell me, how was the video? How was the video? See, like when once I upload video in YouTube, so I think you will get clear, video on. Okay. See, I think this video gave you a complete picture on what exactly the pre-stressing, different types of pre-stressing systems, and one more thing. So you should have a lot of exposure towards pre-stressed concretes by having a lot of industrial visits. So then only you can able to understand better. So that's the reason why I showed this in a form of a video. That's what developed by NITAR Bombay. Okay, it's a National Institute of Technical, Training and Research Center. So which is gonna, work on quality controls majorly. At the same time, they train a lot of students and faculty members towards, latest technologies. So in that way, this pre-stressed concrete, was good in terms of all the latest structural elements, right? So now let's come back to our presentation. So in our lecture 8 we are going to discuss different methods of pre-tensioning and post-tensioning. So yesterday we already gone through Hoyer method, so which is going to useful to do pre-tensioning system, right? So pre-tensioning method. So now we will go with what are the methods and systems of pre-stressing. Okay, so here pre-tensioning we discussed in the previous class, and coming to other 4 methods which are gonna useful for post-tensioning system. One is Magnel method, Freyssinet system, Gifford Udall system, and the McCall system. So in the previous class, we already covered a Freyssinet system. So let me discuss the Freyssinet system again. So then we will go through the other 3 systems. Okay. The Freyssinet system, what we discussed yesterday. So it was introduced by French engineer. So it is the first method who introduced, doing stressing. Okay, in terms of post tension. So here they are using different types of different dias of wires like 5 mm, 7 mm, 8, 12, 16, and 24 mm, which are grouped together. Okay, which are going to be in a form of a cable. Okay, so with the help of a helical spring inside. So this is the system where you can able to see it clearly, right? So here, what the purpose of the spring? So that spring will try to maintain that proper spacing between the wires. Okay, so that where the cable was inserted into the duct. So in this picture, you can able to see it clearly how the Freyssinet anchorage was placed, right? So this is what I am talking about. It is in a form of a cylindrical, concrete cylindrical shape. So where the funnel anchorage with the steel spirals are also placed in between. Okay. So this is what an anchorage cone, and all individual strands are placed within the cone with the help of the wedges, right? So this is what the Freyssinet anchoring system. So how this anchorage device, so which is the consists of your concrete cylinder, okay, so which is going to be spiraled with the steel wire, okay, so where it is going to be concentric conical hole and corrugated on its surface. So here that's completely a Freyssinet double acting jack is going to be used on either side of the element or any girder or a beam, so to apply the tensile forces to the strands where it is going to be induced compression forces into the concrete. Okay, so that is how the first method which was introduced by Freyssinet, okay, to apply this post tensioning into the post tensioning of strands where inducing the post stressing into the concrete. Okay, so that is what about the Freyssinet system. So here you can see all combined together. So this is how the end system was made, right? So the end of the wires are going to be anchored and the other end is going to be pulled till the wires are going to be stretched to the required length. Okay, and the certain inner portion is supposed to be jagged. So okay, so which is going to be pushes into the cylinder to grip the wires. So that is what happens in the Freyssinet system. That is a usual system where they do go for post tension, right? So this combined together, this is how the end system is going to be. And coming to the next system, which is the Magnel Blaton system. Okay, so we have to go in an order where you can able to observe the advantages of each system, right? So the first Freyssinet system. So what is the next Magnel Blaton system is advanced than the Freyssinet system. Here in Magnel Blaton system, in Freyssinet system, several wires are stretched at a time, isn't it? See here you can see there are a bunch of strands which are stressed together. Okay, but what happens in Magnel Blaton system, here your 2 wires are stretched at a time. So all bunch of strands are not going to be stretched. 2 individual wires are stretched at a time. So this method was introduced by a famous engineer called Magnel. He is from Belgium. Okay, so instead of stretching all strands at a time, 2 individual strands are going to be stretched one by one. So that is what this Magnel Blaton system was introduced, where it can able to stretch the wires within the designed force. Okay, so that's the reason why he introduced how instead of stretching all strands at a time, individual wires like 2 or 3 strands can be stretched individually. Okay, that is what he introduced. So in this system, the anchorage device, which is going to be consists of a sandwich plate. So here you can see how it was. There is a sandwich place, upper and bottom jaw, right? So that is where the plates are going to be hold the strand with the help of the wedges, right? So the anchorage device consists of sandwich plate having grooves, right, to hold the wire, and the wedges which are also grooved. So each plate carries 8 wires. So this plate can able to carry 8 wires. So where it can able to stretch 2 wires individually. Okay, so that is what the Magnel Blaton system was introduced. So here you can see it clearly. In between the 2 ends, the spacing of the wires are going to be maintained by spacers. Okay, here you can see the wires are not touching together, isn't it? So you need to maintain some space of each individual wires. So they are going to spacers with wires of around 5 mm or 7 mm, which is going to be adopted. Okay, each wire is to be spaced within the other wire of around 5 to 7 mm. And the cables which are going to be consist of the wires are going to be multiply of around 8 wires. So here the cables which are going to be stretched, okay, which is around 64 wires are also used under special conditions. Okay, so all together like a bunch of strands, so around 64 they are going to stretch two individuals, okay, with the help of Magnel Blaton system. So here the special devices jack are going to be used to pull the wires at a time and anchorage them. Okay, so that you can able to see that in the picture, so where the sandwich plates are holding the wire with the help of the wedges, right? So that is the difference between the Freyssinet system and the Magnel Blaton system, right? I hope you understood what the difference between these two methods. Let's go to the third system, which is the Gifford Udall system. So this is the one which currently we are making use in all heavy structures, like stressing of box girders, like single cell, double cell box girders, and heavy girders, right? So this system was originated in Great Britain, so which is widely used in India nowadays in all heavy constructions. So this is a single wire system, right? So it is a single wire system. So each wire is stressed independently using a double acting jack. So I think in the video you have seen, instead of stressing all wires at a time, each wire is gonna stress individually with the help of uni-axial jack, right? So that uni-axial jack is going to be used to stress, pull the strands individually, right? So that is what the Gifford Udall system is, stressed independently using a double acting jack. What do you mean double acting jack? The jacks will be placed on either side of the girder, okay, either side of ends and matter. So that is how it is going to be stressed individually. So here any number of wires can be grouped together to form a cable in this system, where you can have all these in a single cable. Okay, so that is how there are two types of anchoraging devices. One is tube anchorage, other one is plate anchorage. Okay, tube anchorage in the sense, so all strands can be clubbed together, where it can be called, where it can be placed in a tube. Okay, instead of placing in a tube, you can place each individual wire in a plate also, right? Earlier you have seen how the wire was placed in between two sandwich plates, right? So there two wires are stressed at a time. But here, while placing all wires individually in a plate, each wire can be stressed easily. Okay, so that is the reason why plate anchorages can be used to stress individually, so better than the tube anchorages. Okay, tube anchorage in the sense all wires will be clubbed together in a form of a cable, where they are going to be inserted into a sheathing or a duct. Okay, even though they can be stressed individually. Okay, that is what Gifford Udall system is talking about, right? So this is how you can see. So this is what a tubular stressing, right? So all strands are there in the sheathing pipe, so where you can stress these wires individually in terms of this Udall system, right? Gifford Udall system. So there will be spiral reinforcement, so where it is supposed to be provided at end block of the girder to carry heavy stresses which are going to be located at the end support, right? So here the tube anchorage is going to be consist of a bearing plate, anchorage wedges, and anchorage grips. So you can able to observe it clearly here. This is how the tube anchorage, here there is a spiral casing, and there is an anchorage cone, and there will be a bearing plate, there will be wedges, and there are the strands. Okay, so that is how in tubular anchorage system there will be a bearing plate, anchorage wedges, and anchor grips. So where the anchor plate may be square or a circular, or sometimes it is all depends on the how many wires you are going to provide. If there are bunch of wires, you have to go with a circular system. If there are only few, where you can go with a square system. Okay, so which are around having 8 or 12 tapering holes within the particular casing, right? So in addition, there will be a grout entry hole which is going to be provided in the bearing plate itself to grout the sheathing pipe after completing the stressing, right? and there is a tube unit which is going to be fabricated steel component which is going to be incorporated in a thrust plate. So why? Because there is the steel tube which is going to be surrounded with some helix and a helical spring and mother. So this unit is going to be attached to the end shutters to form an efficient cast-in component of the anchorage. So that's what you have seen in the figure number 5. So here you can see how the tube anchorages was placed so within the anchorage cone, right? Here there is a thrust plate. This we call it as a bearing plate and a thrust plate and there will be an anchorage plate and there is an anchorage grip which we used wedges over there. Okay, so in all systems the setup of materials and the stressing materials setup is everything same. The only difference is how you are doing stressing. Are you doing single strand stressing? Are you doing double strand stressing? Are you doing multiple strand stressing? That is how the systems are varied with the help of Freyssinet or Gifford Udall system and Magnel Blaton system, right? So this is how the systems vary based on the type of stressing, right? Or a system of stressing, I can call it as. And coming to the last one, which is a McCall system. So here you are not going to use any kind of strands. Here they are using reinforced bars. Okay, so this method is used to pre-stress steel bars. Okay, see, as I already told you in design of steel structures, have you gone through the bolt? We are having two bolts, right? One is a bearing bolt, other one is HSFG bolt. What do you mean HSFG bolt? HSFG bolt stands for high strength friction grip bolt. High strength friction grip bolt is supposed to be pre-stress. Okay, so why? Because to carry heavy loads. So that is how the steel bars can also be stressed. So that method is called McCall system. Here the diameter of the steel bars are going to be around 12 mm to 28 mm bars are going to be stressed, which are going to be provided with the threads at the ends and inserted into the perforated ducts. Okay, so with the help of that kind of threaded rods, they are supposed to be stressed together. So here, after stretching, the bars are going to be required length, they are going to be cut and tightened using nuts. That is how these kind of stressed steel bars are going to be used for in terms of bolting, in terms of HSFG bolt, which we use for heavy connections. Okay, so that is how we use the HSFG bolt in steel structural connections. So there the pre-stressing technology or pre-stressing system was used, McCall system. Okay, so in the picture you can able to see how the steel bar was stressed with the help of McCall system where the threaded rod. So once the rod is stressed, you can cut into a required length and you can make use of that rod in terms of bolts. Okay, so with the help of a washer, there will be a washer, there will be a bearing plate, and you can see where the nut was threaded. Okay, so everything you can make use in a form of a bolt. Okay, that is what the McCall system, right? And the other methods of systems which we already seen in the video. What are the other parts of stressing systems apart from mechanical stressing system? There are two stressing systems. One is electrical stressing system, the other one is chemical stressing system. Okay, so let's talk about what do you mean electrical stressing system. I think you have already seen how the electrical stressing system was made, where the rods are supposed to be subjected to high temperature, so where it can able to stress. Then after it is going to be cooled down, so where it is going to be squeeze the concrete to its required design. So here in electrical pre-stressing, reinforced bars are coated with the thermoplastic material, and such kind of material like sulfur or low melting alloys are going to be buried in the concrete. So that is how after concrete is set, electrical current of low voltage with the high amperes is going to be passed through the rod. Okay, I think in the video you have seen how the electrical pre-stressing was made in terms of pre-tensioning and post-tensioning. Pre-tensioning in the sense you are going to supply the what we call electrical current of low voltage to the rod, where the rod is subjected to having a temperature inside. So then after where the concrete is going to be poured, when it is cooled down, so definitely concrete will be subjected to squeeze. Okay, so in this electrical current heats the bars and the bar elongates, as we know. So whenever when the bar is subjected to electrical current, obviously the bar will try to elongate. So here the bars are going to be provided with the threads at the other end and tightened against heavy washers. After required elongation is obtained due to this electrical current, then the bars are going to be cooled down. There the pre-stress develops in the steel, which is going to be stress the concrete, okay, where the bond is restored by solidification of the coating. Okay, that is what going to happen. See, for this best example, I can say, let's take a small rubber band. Okay, pull the rubber band and put it on your hand, like on your hand. So once you release the band, so what happens? It will squeeze your hair which was there in the hand, isn't it? Right? Have you tried that in your? Have you tried once? ఓకే, మీరు అందరు చిన్నప్పుడు ట్రై చేస్తుంటారు. సో రబ్బర్ బ్యాండ్ ని మనం ఇలా పుల్ చేసి యూ కెన్ పుట్ ఇట్ ఆన్ యువర్ హెయిర్డ్ హ్యాండ్. సో ఆఫ్టర్ రిలీజింగ్ ద ఫోర్సెస్, వాట్ హ్యాపెన్స్? ద రబ్బర్ బ్యాండ్ విల్ ట్రై టు wind with the hair. Okay, that is what going to happen in the electrical pre-stressing. When it is electrical current is supplied into the rod, after when it cool down, it is going to be squeeze the concrete. Squeeze in the sense it is going to have the pre-stressing into the concrete. Okay, so where it is going to be restore the solidification of the coating also going to be takes place. So that is what exactly the pre-stressing elements. I think the applications you have seen, pre-stressing is going to be used in different applications of, like, curved slabs, so these are the elements where you can able to go for chemical pre-stressing. Okay, sorry, electrical pre-stressing, right? And let's talk about the chemical pre-stressing. Here chemical pre-stressing is going to be done using expanding cement. So even in the video it was very clearly mentioned how the chemical pre-stressing was done in 3 different methods, isn't it? So in the 3 different methods, when you start using this expanded cement, so then when the cement expands, obviously the concrete or the element which was placed in between the expanding cement, it will get crushed, it will get compressed. So when it is get compressed, automatically the element will become hard, it will bend towards upward direction. So this kind of chemical pre-stressing can also be used nowadays, right? So here the pre-stressing can be applied by embedded steel in concrete made of expanding cement. So where the steel is elongated by expansion of concrete, and thus it is going to be pre-stressed, right? So steel in turn produce compression stresses in the concrete, we all know. So that is how the chemical pre-stressing is going to be used, okay, where you can compress the concrete with the help of expanding cement, right? So let's see the examples. Here the chemical pre-stressing is also called as self-stressing or chemical stressing of concrete, right? So here what kind of chemicals are to be used to make your concrete chemically stressed, right? So here you can see it clearly. It was made possible by the development of expanding cements by Loiser of France. So Loiser is a scientist who developed and who first introduced this chemical pre-stressing into technology in 1944 itself. So where they are using generally expanding cements, which is consisting of 75% of Portland cement, which usually have in the cement, and 15% of alumina cement and 10% of gypsum, so which results in formation of calcium sulfoaluminate. So this is the combination which makes your cement to expand. Okay, with that expansion only the concrete will get squeezed in between the expanding of cement supports, right? So you can see the examples also. This chemical pre-stressing is generally suited for elements like precast beams and columns. So nowadays you can see there are a lot of precasting elements are going to be manufactured, isn't it? So they are using this kind of chemical pre-stressing. Why? Because it doesn't require any kind of mechanical setup. You doesn't require any kind of jack, you doesn't require any kind of bearings, okay, wedges, strands, nothing you require. You just require expanding cement where you can go with the chemical pre-stressing. Okay, that's why lot of precasting beams and columns, okay, are going to be post tensioned with the help of this chemical pre-stressing technology, right? So it has been found that structural elements ideal, like thin walls, slabs, shells, even concrete pipes, okay, folded plates, composite columns, these are all which are going to be precasted, okay, nowadays. So these all are supposed to be chemically pre-stressed. Okay, so there are no certain pictures and certain videos particularly for chemical and electrical pre-stressing, but the video which I have shown earlier, there it was clearly shown how the chemical and electrical pre-stressing was done with the help of post-tension technology, right? So this is what about the different types of methods and systems there in pre-tensioning and post-tensioning, right? Okay, guys. So I think showing this video gave you a clear picture on all these types of systems like Freyssinet system, Gifford system, McCall system, Hoyer system, and all these electrical and chemical systems, right? So this is what about the different types of systems which are going to be used in pre-stressing technology, right? That's it, guys. That ends with the presentation. So any doubts, you can ask me now. I hope that video gave you a complete picture in understanding different types of stressing systems, isn't it? Right? So there won't be much difference in all the systems. The only way is how the way you are stressing. Or it is stressing single wire, or it is stressing 2 wires at a time, or they are stressing all bunch at a time. So that varies different systems. That's it. End of the day, everything is going to be stressed, okay, with the certain design loads. That's it. So we are having 2 minutes time. So please, guys, any doubts you can ask me now. So tomorrow we are going to start with the losses of pre-stress. Okay, we need to focus mainly on that. Why? Because for going for the design, you should go with the different types of losses of the pre-stressing. Okay, we'll spend more time. Clear? Vamshi, very clear. Thank you. What about others? So please respond, guys. Any doubts you can ask me now. Just 1 or 2 minutes. Anyone? Guys, are you clear with this? Are you clear with all systems? So very important question in external examination also. Okay, they may ask you individual system, or they may ask you to write all the systems there for pre-tensioning and post-tension. Okay, so where you need to classify that into what are the mechanical pre-stressing systems, and what is chemical pre-stressing, and what is electrical pre-stressing, right? So in that way you have to write nicely. Okay, anyway, I'm gonna give same question for your assignment also, where you can represent on your own. Okay, yeah, so I think everyone is clear with this. Okay, then, so it's already time now, so only 1 minute left. So clear, right? Okay, then I will try to share this presentation to you guys, so by that you can view it again. Any doubts you can ask me in the tomorrow session, right? Okay, then, thank you so much. So stay safe, guys. Tomorrow we are going to start with losses of pre-stress, which is the second part of the second module. Okay.